ITC Pizza Lunch. Today we actually have two visitors talking to us. The first is Victor Pankratius. I mispronounced that actually.
No,
really?
good.
Okay. Pankratius, who is the leader of the Astro and Geoinformatics group at MIT Haystack. And so he'll be talking to us about computer-aided discovery in astronomy. Thank you.
Thank you very much. Is this muted?
Is it on?
Okay, it's on. Thank you. Okay, thank you very much for an invitation and for this opportunity to talk to you. So first off, I'm a computer scientist by training with an extraordinary passion for astronomy, and that's how I got into science and actually making this as a job for me. So I really like interdisciplinary science, and you will see that the kind of work our group is trying to do is merge the fields of computer science and informatics with other fields like astronomy. And I think there are a lot of advantages in doing this. So please bear with me later on when I present the astronomy case studies that I'm not an expert in most of these fields, but I would like to keep this interactive and get feedback from you about the potential and maybe some special things that you would see as beneficial. So one starting point that we were looking at is that there's a lot of data everywhere. And this is not new, but it's getting worse in recent years. And I would like to dramatize this a little bit and say, well, we have a data tsunami coming. And if you're looking at the kinds of instruments we're talking about in the future, like the square kilometer array or the LSST and other kinds of instruments, they will all generate tons and tons of data. And traditionally, scientists, and specifically astronomers, have been used to doing things in a certain way. But now we have to think about scaling what we already do in order to cope with this data. And the way we're thinking about this is we want to give astronomers the tools they need to be able to scale in this new world, which is predominantly data and software based. And we want to provide tools that keep the human in the loop. So whenever I talk about automation, we're not attempting to replace the human scientist, but actually give the human scientist more power. And as everything is being digitized these days, necessarily you will have software-based instruments and backends. And in this scenario, there's a very difficult gap to bridge. On the one hand, the scientific gap, but on the other hand, we don't want everyone to become a computer scientist who's totally apt in parallel computing and algorithms and all these things. So we need something in between that bridges this gap in an acceptable way. This is difficult, and there have been attempts in the past that worked or did not work well enough. And I think we need to tackle this challenge because otherwise it's going to be very difficult to create new insight in the future. So if you're looking at this process, what are discoveries about? We believe that it's basically a search process, but it's a search process at different levels of abstraction. And if you're looking at this from a semiotics point of view, you have here at the bottom the real-world phenomena that we're interested in, that we're trying to measure or describe in some way. And the empirical process with instruments generates signals and data, but this data is essentially just an encoding of the real-world phenomena. The next step would be to identify certain features through data exploration, analysis, and data mining. This is mostly the semantics abstraction. In my opinion, this is where most algorithms and techniques are today. They come up with some technique, say some data mining technique, and then it says all these pixels in these images might be interesting for you because they might pertain to a certain phenomenon. But these algorithms, however, don't know much about the physics involved or the deeper implications, which is why they would produce many false positives or they have limited use in practice. So for insight generation, there's still the scientist who needs to make this connection. Oh yeah, this algorithm said this is interesting, but why is it? Does it have any meaning? How does it fit into theories? Is it something new? Does it falsify something that we already know? And so on. And this is the actual level that we want to get to if we want to scale with more data. So we want the pragmatics level to actually have more automation on the insight generation side to say, what does this feature imply? Does it fit into a theory? Does it falsify anything? Is it anything new at all? Or does it contradict or confirm established models? And with some help and some work, I think we can get there. And I want to outline an approach that we are working on right now that can help in this process, help the scientists make this process more efficient. So, whenever you disagree with me, feel free to interject or say something, please. So we see this process as a search process because phenomena are mapped to data. So then it means if we want to make new discoveries, we have to search for things in data. And for this, we want scalable machine assistance, in particular because we need to overcome human cognitive limits. If we're talking about petabytes per second of data from future SKA instruments, for example, the square kilometer array, or the LSST that's going to generate a huge database with many images, it is very difficult for a human to just inspect all these elements. There has to be something that helps in prioritizing or making decisions. So one thing that we want to do different and where this approach is trying to infuse physics knowledge in this process is that we have two sides. We have the theory side here at the bottom and the empirical data side at the top. And the way we want to scale the search is basically by already having a model which can be configured and parameterized by a scientist. So say, for example, you're looking for a certain phenomenon or a certain shape of a galaxy or some other thing that you know from theory how it could look like. However, typically you have ranges of parameters where you say, well, I don't know if it looks exactly like this, but it might look like this or like this. So imagine you have like sliders in this model, and these sliders have ranges. And these ranges define a search space for you. So the search space can then be searched systematically by, in principle, generating different variants that you think might occur in reality, and then having some kind of intelligent system take these patterns and looking up in empirical data to see if there's a match. So one reason you want to do this is because suppose you find a match, and we have shown this to work in several areas in geoscience so far. So the astronomy side is work in progress for now. So suppose you find a match, then you already have the link to the theory. So you have an explanation that the phenomenon that you found in certain data collected by various instruments are linked, for example, to specifically this model. And the reason why you found that and what it means is defined by these parameters. So you're creating a whole chain of explanations that goes back into theory. And this is different from pure data mining, where the data mining would pop up at some point and says, well, I found something like this, or maybe something that is distorted in a way that's not even interesting for you. So one thing you can do in this process is make the search more intelligent, because as you can imagine, there's many options to generate models like these. So essentially, you can think of this like a tree. Like in chess, you have different moves that you can make. And some moves are more promising that lead to actual discoveries, and some moves are not. So in this process, while you're searching, you can use machine learning to kind of prune this tree and concentrate your search in an area that might be more promising. And one way to get feedback in the search is from the scientist. The scientist can be presented in certain cycles with things that have been discovered so far. So the scientist can give the feedback, yeah, the system says, well, I found something that looks like that, but it's not exactly like that. Do you want more like this, or like this? So there's one way to refine the search. And other ways can be more automated based on functions or criteria where you can specify, well, what is my objective function of the search, which can be an optimization process. You would optimize to find certain things that reflect certain theoretical assumptions. So this is like a very rough overview conceptually of what we're doing. And we're building the system right now. The system runs in the cloud because we want to move away from a world where we have to download data to our laptop, do something to create the results. This is not going to work with petabytes of data. So the data has to stay in the cloud, and the computation has to move to the cloud to where the data is. And the interface that we provide is a cloud-based web interface. Right now we are using Python because we thought scientists like Python. Astronomers like Python, though they also like Fortran. But we believe Python has many advantages simply because there's a big community out there, there are libraries, there are things easy to reuse. And all what I described right now can be expressed in Python. So you can express a model in our Python interface. You can express ranges of parameters, and on top of that, you can also express algorithmic choices. So for example, when you're thinking of detection pipelines where you have raw data coming in on one side, say images or signals, you apply some filters, and then on the other end of the pipeline, you're getting something like this. Well, the system can also perturb this pipeline according to options that you can specify as choices. So you can say, instead of a median filter, I have a set of choices, which can be a median filter or some other kind of filter. If it's an analysis, you can say, well, I want a principal component analysis or an independent component analysis, and so on. So this is important because if you're making the wrong choice, which may happen if you're making an intuitive choice, you might make no discoveries at all. And I want to show you an example. This is from geoscience, but I'm also going to show you astronomy examples. So this is total electron content in the ionosphere at a given time. And this total electron content tells you something about how many electrons there are above you in the ionosphere. And this data can be fed into different pipelines to create visualizations. And depending on the choice you make in this pipeline, you get one of these 4 visualizations. So each one shows the same raw data set. Okay? But as you can see, if you're making the choice to select a certain filter, you might highlight large-scale phenomena, like here on the upper left side. Other filters might highlight noise more or smaller scale phenomena, and other choices might highlight nothing at all. And the problem here is that for small examples, you kind of know what to choose. But if you have a lot of data, if you have a lot of complexity in your models, how do you know what the right choice is? Okay, there's typically many assumptions that you make intuitively, but your intuition might be misleading. And this is what I mean by overcoming human cognitive limits, because people think, oh yeah, that's always what we did. That's always how we choose this parameter. And then you get that kind of image, and your image detection says, well, I don't find anything in here. So this is why machine support can help you explore the options of the search space that you have. Here's an example. This is not implemented yet, but examples from the literature where the choice of algorithms can affect the results. So here, for example, you see the spectral energy distribution of galaxies. And these are eigenspectra determined from a sample of 2,000 Sloan digital galaxies selected at random. And here at the top, you see the mean spectrum of a sample. But the columns are different algorithmic choices. And then the rows below show like different eigenspectra obtained by applying 3 different principal components analysis algorithms. And as you can see, depending on those choices, these eigenspectra might look very different. So your choice how to process some collected data affects the outcome and your ability to actually make discoveries. Another area that I find highly interesting is structure detection. Just because there's many algorithms that you can choose from, how would you find galaxy clusters, groups, filaments, and other things that are important to study cosmology and galaxy evolution? And then suddenly you're in computer science where you have a big toolbox of things. And what you want to do as an astronomer is say, well, I have this toolbox. Here I would have to find some kind of density increase or some kind of structure. So all you want to do is take the data and then let the system decide based on the number of choices which one to apply, and then choose from a mosaic-like result which one you think applies best to solve your problem. So how does that actually work? So this is a little bit more detail. What we do to create the search is we have a basic model with parameters. So it's a parameterized model that is expressed in Python. And we have a modeling language that helps abstract away a little bit from code. So what you want to do is you want to say, I have some synoptic model that spans like everything that I want to try out. I have various submodels. And then you want to say, in one specific variant that I want to explore, I have things that have to be in every variant, things that are optional, and things that are an alternative. And then the system takes that description and generates actual pipelines and model variants that are tried on different empirical data sets. And these models, aside from the algorithmic choice, would also contain different parameter ranges and span the search space. So we started building these kinds of models for various areas. This is a radar imaging workflow, for example. But we're continuously expanding this library and this infrastructure to be able to cover more. And right now, we're exploring astronomy as an application area. And there's, of course, many things to do there. As an output, for example, we can generate heat maps. So this is an example that we used in volcanology. And here are choices in a pipeline that process time series data collected by GPS sensors on volcanoes. And depending whether you choose a processing pipeline with a median filter or a Kalman filter with certain parameters, you would get models that lead to more similar results than others. So the heat map here tells you which models lead to results that are kind of similar. And depending on the choices, you can kind of see different classes of models emerging. And that is something where the scientist can pick up again and take these candidates. So if you want a cluster, so we say, okay, this looks like model type number 1, this looks like model type number 2, and this is type 3 or something. And these all represent alternative explanations of the empirical data. And then the scientist's job is to find out, are these alternative explanations actually real? Does it make any sense? Or is it just an artifact produced by the system? But at least the system lets you explore more systematically what other alternative hypotheses you could create that explain the same data sets. So I just want to throw out in the last couple of minutes some case study examples where we believe this could be really useful in astronomy. One is stellar population synthesis models. Is anyone here working on that? Okay, that's good. Then astronomical object detection, galaxy morphology, and exoplanet search. And what I want to highlight is in these areas that you really have a number of choices that you can make in how you make assumptions about the models, how you process the data. And in stellar population synthesis models, what you want to do is you're looking at a galaxy's spectral energy distribution, and then you want to trace it back to components in this galaxy, like components that lead to the sum of things, right? So then you want to be able to explain, why do I have this, this overall energy distribution? How is that composed of different stellar populations? So in this context, you would have like an initial mass function. You would evolve stellar population using stellar evolutionary tracks, and then generate the resulting spectrum from a stellar library, because then you know from the individual stars how their energy distribution looks like, and you compose everything together to get the sum. And there are many things you can assume. In the first case, well, how does the initial mass function look like that describes the mass distribution of stars? You see that's already 3 options there used in the literature. Then for the stellar population synthesis models, there's several options as well that people have been working on. And then for the third step, there's telespectra that can be obtained from either theoretical or empirical libraries. And the end result is something like this. So you have the empirical measurement, but the red part here is what the model would predict. Okay? So now let's assume that the computer-aided discovery system can generate this red line. Then you can use that as a query to query the empirical data from empirical measurements. And suppose that this was a match, so this red line here was a match for this particular data, then you could go back each slide and trace it back exactly what that means. Maybe it means that you have this kind of distribution. Okay? So that's a lot more insight rather than just fitting lines to models and having some function in there. Okay? Because this tells you how is the stellar population composed. Another area which I think is interesting is object detection. Because object detection sounds simple. The automation is very complex, and it has various problems. But I just want to throw some literature examples at you, how many different techniques and filters have been applied for different kinds of object detection. So if you're having new images or a new project, you don't necessarily want to try out all of these manually. You would like to have a system where, say, here's my new raw data, and please apply a pipeline where the system tries all of them out, or the ones that are more promising based on the machine learning approach I described, and then shows you the result that might be interesting. In a very similar case, I think galaxy morphology applies the same techniques. And finally, just to leave some time for questions, there's another area that is interesting, which is exoplanet search. Is anyone doing exoplanets? Okay. So very similar case there. I won't have time to go into details, but when you're looking at light curves, those light curves are the sum of different properties, of different physical properties that lead back to the physics, why they look like that. So look at these different components here. And if you had a computer-aided discovery system, you could vary these components that lead to a certain sum and then match that against the actual data. So if you find a planetary system with a shape like this, you might be able to trace it back to why you see that shape. Okay, so this is the kind of automation that points the scientist in the right direction. This is not meant to explain how it really is, but we believe this is a good tool to help scientists become more efficient in the search and maybe see things that they haven't considered before. So to conclude for today, I think that software-defined instruments that generate data will automatically force everyone to have some kind of software-based data processing in place. The scalability of data also means we have to scale our techniques and tools in the way we do science in the future. And that will have to match with the data collection rates that we have today. And then I think we're on a good way to also scale the discovery search. And I think this is very exciting and very interesting. I'd like to thank our sponsors who believe in us. And so far, the results look very promising. And I hope that maybe through discussions here, if you want to talk to me, we are always looking for new case studies where we can apply this kind of technique and maybe help you in your project make some progress. So thank you very much, and I'm looking forward to taking your questions.
All right, are there any questions? Yeah.
So, how at the beginning you mentioned taking models and then sort of graphing onto a massive parameter space and comparing them. How do you handle model sets that are either too finely generated or too coarsely, or both in different ways? How would you sort of interpolate between them to get better precision in your results?
So currently we rely on machine learning algorithms, and there's different search strategies. One thing that can happen there is that you get stuck in a local minimum, and then you generate two similar models or models that don't lead to new insight. So this is actually a bigger research area, but generally speaking, the way we solve that is we can use evolutionary techniques. So if you have results that are too similar, then you can perturb certain parameters. So you can do a kind of sensitivity analysis and see if I change certain parameters, then the results are more different. And then you can generate models that are more different than the others. And then you avoid generating, say, many, many models that are very similar and just one that is very different. The other technique that we believe needs to be included is human scientist feedback. Because otherwise, I think the attempts to automate everything won't work, because sometimes you really want to guide the search in a certain direction. And I think human feedback will be the key into fine-tuning this algorithmic search. We can think of crowdsourcing, for example, also, rather than just one scientist.
All right, I think we have time for one more quick question.
Well, I was surprised that in all of this talk I didn't hear the words data reduction. And you didn't say those words, and in my experience, that's where things usually get stuck.
Yeah. I'm careful avoiding words that might have negative connotations, or I don't like the word data reduction. That's why I was talking about data processing pipelines, because if you're reducing the data in inappropriate ways, you're reducing your actual information away. So I'm looking at this as an optimization problem. What you want to do, ideally, you want to maximize the information content per byte in the data collection, and then you want to preserve the information per byte for the phenomenon you're looking at. And this is an optimization process. So if you're reducing the information content of the phenomenon you're looking at in this process, then you have a lower chance of making a discovery. I'm looking at this as an optimization problem.
Okay, well, if there are any further questions, you can ask Victor over pizza. Let's thank him again. All right, so for our second speaker, we have Erik Rosolowsky, who is visiting us and is a professor at the University of Alberta. And he's going to tell us about simulations and observations of
That's the one. Oh. Good afternoon, everybody. Oh, I'm loud. Sorry, it's lecture voice. There we go. It's a pleasure to be back here at the CFA. Yesterday, I gave the large-scale seminar, and I talked about an arc that was generated in my postdoc here at the CFA. And this is another arc that was also generated here in my postdoc at the CFA. So both of these talks you can blame Alyssa for. In her offhanded way, she said, one day, I'd like a good way of comparing simulations and observations. And we generated several proposals of various stripes to actually try and go and do this in a rigorous fashion. And I continue to think this is an amazing idea, even if the NSF may not. And we've sort of carried on in a route of trying to do this. And this really rests on a fairly interesting collaboration we've generated. All of the work I'm presenting here has rested on the work of my graduate student, Erik, who's written much of the code that's going to drive what you see here. And it's a collaboration between me, ignorant observer, Jason Lepke, who's a statistician, and Jason's specialty is in the notion of experimental design, which is the idea that he got, or that he worked with, at Los Alamos. And we know what they do at Los Alamos, except they don't get to blow up things anymore. They get to run extensive computer codes and then figure out, optimize the computer codes to do what you want, say, level cities in the most effective way possible. But he is interested in actually running numerical simulations and comparing them and figuring out how to change their inputs to produce the ideal outputs in an efficient fashion. And I worked with him when I was at UBC, and I realized, wait a minute. Changing inputs to produce outputs that match your ideal conditions, this is wonderful. We can work with this. And of course, I don't do simulations, so I worked with Stella Offner to get us started here. And Caleb Ward was another student at UBC who did a lot of this effort. So that gives you a little of the groundwork for how this collaboration came to be. But our basic product is that we have observations and simulations of the interstellar medium. And what we want to do is figure out which conditions that are governing these different simulations produce an optimal match for those cases that give you what you see in the interstellar medium. And I view this, after traumatic years of real analysis as a math minor, in the terms of a domain diagram, where we have a physical domain, and that's the actual universe, what's out there happening. And, as is pointed out, what we actually see is not the physical universe. The map is not the territory because of effects like radiative transfer and telescope corruption of the data. We get observations. And what they pay me the modestly big bucks to do is try to invert this domain reduction, where they say, well, you've got all this lovely data, go backwards, tell me about the physical universe. And normally, what we do when we're dealing with this is we're looking at data sets of position, velocity data cubes. So this is a carbon monoxide map of a star-forming region called NGC 1333. And what I want you to remember through all of this is the data that I work with are usually these spectral line data cubes, where every pixel in this map actually represents an observed spectrum here. So what we do in astronomy typically is we say, okay, these observers have said, oh, the temperature of these regions is about 10 Kelvin. And we say, and then you walk over to your numericist simulation theory expert and say, 10 Kelvin, your temperature is 10. And they plug that into the initial conditions of their simulation and produce some insight because, of course, simulations are the way we get to play the universe forward. And that simulation requires a lot of important inputs. The nature of turbulence, the significance of gravitation. How important are magnetic fields in this area? What are the effects of the chemistry underlying this? Because these are molecular clouds, and they have time-varying chemistry. And ideally, you would like to have some sense of live radiative transfer, because stars will, through their radiation and momentum inputs, sculpt these star-forming regions. So we would really like to provide parameterizations that say this is the right physics to put into your simulation with these parameters. But the contention that we made in the taste testing domain and moving forward is that the right place to actually affect this comparison is to not to try to invert this reductivist mapping from the physical universe down to the observational domain, which we understand the mapping, but we also understand that it's lossy. What we want to do is to actually apply the same horrible corruption of reality, come down and generate fake observations. And we can actually do this quite reliably. Well, at least far more reliably than I can tell you the three-dimensional structure of a molecular cloud in gas with an understanding of its velocity. So this is our overall strategy. This time, in this talk, I'm going to talk about work that we're using to come up with the tools to actually make this comparison between simulations and observations. And where this is entirely a simulation-based talk with a little data at the end, and we want to sort of figure out the tools that we have to make this comparison. So when we're talking about this idea, we use the notion of a metric, which is a measure of similarity between different data sets. And we have gone into the literature and we found a ton of different comparison techniques that we think that people have asserted this is a useful way of describing or reducing the information in a simulation. We've then gone ahead and created a bunch of different simulations with a huge range of initial conditions. Not a huge range, but a huge number with a bunch of different initial conditions. And what we're trying to do is if we understand, if we change the physics, do we see, under that reduction, a change in the simulated observation output and this comparison metric? We've gone into the literature and we've come up with a suite of different comparison methods, and they broadly fall into three different categories. On the top, we have methods that generate object or descriptions of the things in the interstellar medium, or in the data, I should say, and how we actually describe that in terms of catalogs or structure. Then we have a bunch of methods that were drawn from turbulence and turbulent analysis, and they are inspired by trying to recover the properties of turbulence in the interstellar medium. And then we have the idea of measuring the distributions within the data. For example, the probability density function of the intensities or the velocities or something like that. As an example, here's one of my favorites. This is the spectral correlation function, another technique, or another thing that came through Alyssa. Alyssa's kind of focal in all of my the research graph that I do. But this is a project that I worked on as an undergraduate, and the idea between the spectral correlation function is that you want to take these spectral line data cubes and compare a spectrum at one position to its neighboring spectrum. And this is essentially an overlap integral where you compare this spectrum to this spectrum and it quantifies how similar the spectra are to each other. And then you figure out that similarity as a function of separation. So this moves into a lag domain where this is difference, spatial separation on the coordinates, and a measure of how similar things are, with white being unity and then falling off as you get farther apart. What we're doing is we take the spectral correlation function information and then we compare this surface in terms of a lag space, where it's position offset in the x and y coordinates, to a different simulation, and we actually just make a single numerical measure of the difference between these two surfaces by just saying, I'm going to add up all these values, weighting them accordingly, and turning it into one number. So now, given position, velocity data cubes, I can tell you that the distance between them is some single number, 3, under the spectral correlation function. And so that allows me to leverage these techniques of experimental design. So let's see what actually came out of doing this. We ran a bunch of simulations using ENSO. They're MHD simulations. We're running a lot, so they're not high-end simulations. We used a 128 cube root grid, fixed pattern turbulent driving, and then we stirred it for a couple crossing times. We turned on gravity and AMR, and then let gravity do its work with refinements and some sync particles inserted. We then generate false state or simulated data by using RAD-MC3D. So we post-process to produce spectral line data cubes like what I showed you earlier, but just of simulations. Our experimental design was to study several different parameters here. And these are the parameters that we're sort of fiddling back and forth to try to see a signal in the data. That includes the shape of the turbulence, this solenoidal fraction, how strongly it's driven, that's the Mach number. The Varial parameter is how significant gravity is, in the sense that low is more strongly gravitating and high is weakly gravitating. The plasma parameter operates in a similar way, where a low is strongly magnetized and high is weakly magnetized. And then the driving scale is the scales on which we inject turbulence into the interstellar medium. This is large scales and then small scales. And we only do 2 levels because we need to run every combination of parameters between these 2 different levels. And so if there's 5 parameters, 2 levels, 32 simulations. And then the other thing that we do is we run these things called fiducials, which is we go to the center of the simulation space and run 5 simulations with different random seeds for the turbulent driving as a way of measuring the uncertainty here. So we have definitely traded quality of simulations for quantity, but that quantity is important for our technique. So every simulation we have is a sample in some high dimensional, in this case 5 parameter space. And so we have Varial parameter and so forth here. And simulation's a single point. And traditionally, if you're doing simulations, you want the best simulations you can do. And if you're doing the parameter study for physics, what you look at is the fiducial, which is your baseline, what you think your best guesses are. And then you turn up the Mach number and see what happens. And then you say, that is the effect of increasing my Mach number. What we do instead is in this work, we do what's called a full factorial design. And that exhaustively searches all the combinations here, just in case changing 2 of these simulation effects will produce a nonlinear response in your results. So clearly, if you're doing a 1 factor at a time simulation, you can really interpret what we call the main effects. So that's the case where you're looking and seeing what, say, the Mach number is doing. And it means you can run the highest quality simulations that you can, because you only have to run your fiducial simulation and a small number of perturbations. On the downside come the statistics effects. You can't estimate the uncertainty, your systematic errors in this analysis. You can't estimate any interactions between your physical parameters. And if there are interactions, you are always uncertain as to the nature of the underlying effects in the simulation. Full factorials, they're great. Why doesn't everybody do it? Well, that's because it costs 37 simulations just to explore 2 levels of physics. And we do get this wonderful statistics side. So maybe we can hybridize these 2 approaches. Foreshadowing. So here's an example. These are 2 different one of our fiducial simulations. These are PPV moment maps of our PPV data set. And this is what we see in the observational domain. And I can look at the case where I have 3 simulations turned here with the Mach number set to high. So what you'll see here is I have a set of parameters where I use this kind of string of parameters, and 0 and 1 to indicate low versus high values. And here's 3 simulations with the high Mach number. And what you'll see is that you can see the effects of changing. This is short scale and large scale driving. And you can see the effects of that. And then you can see the effects of magnetization versus low versus high with respect to high Mach number. Similarly, I can show you the value with the Mach number set to the low value, and then looking at a few different slices here. And the particular thing I want to call your attention to is this Varial parameter combination. So this is going to be a weakly gravitating simulation versus a strongly gravitating simulation. And what you should notice is that you can look at the cases with the Mach number high and then the Mach number set low, and you'll see that there's actually a significant change when you have, and this makes sense, that if you have weak driving and no gravity, you get very little structure. And that effect's actually nonlinear. These two effects will combine together so that high driving with strong gravity produces the most structured data sets. All right, so we get this full set of simulations, and I'm going to show you our results in this view, where we have these sort of parameter strings, all of them running along here. Over here, we have the fiducial simulations, and what we're doing is we're comparing these. These are distance measures, one simulation with respect to another simulation. And what we see here is we're measuring the distance here between the fiducials. And you can see that the different random seeds don't produce a lot of change under whatever statistic this is. It's the spectral correlation function. So we see there's a good, sort of a measure of our error. This is just the systematics intrinsic to the cube. And then as I change my physics to different values, I get different distance responses. And the SCF sees these simulations as different from the fiducials. And the different traces are comparing to the 5 different fiducial simulations. And so this patterning here, actually, you'll have to parse the binary to actually figure out what physics is most important and what the SCF is doing for you. Or we could model that, and we'll do that next. For comparison, some of our simulations look like this. And that's not really a clear physics response. Or this isn't simulations. Some of our measures or metrics look like this. And here we have a large error in the simulation, intrinsic, so just comparing something with identical physics but a different realization of it gives me some uncertainties. And then, mess. So, but we can actually go through and you can use this as a criterion. We want things that look like this, not like this. Quantifying that, we come up with a set of things that seem to work pretty effectively for our particular problem under our parameterization. And then we sort of summarize our results here. And this is it's beautiful to me. But what you see here is that this is a graph, or a heat map, I guess, showing the T statistic, which is how significant a specific measure's response is to changing physics. And what you can think of this is n sigma result. So clearly it's a 10 sigma result, means it's very strongly significant with respect to the errors in our analysis. And then you can look at the different statistics and see along the bottom what they're sensitive to. And I reported here the main effects. So is it significant to Mach number? Yes. All of our good measures are sensitive and responsive to changes in the Mach number. Or plasma parameter, well, you don't want to use VCS if you care about the plasma parameter, for example. The other thing that we actually detect are the interaction effects between, in this case, Varial parameter and driving scale, Mach number, and Varial parameter. And these are things that the physical problem has injected covariance into the problem. High Mach number, strong self-gravity, more structure. And we can say that these measures also detect that covariance. We also, because we're good observers, go ahead and add noise so that it looks roughly like the original data sets that I do. We repeat the analysis, and the statistics that are there change a little bit as to what we can see. So, we have now come up with a good set of measures. We've calibrated our metrics, and we have our suite of comparison between simulations and observations. So our next step is to actually compare to data. And we can do that by actually saying, well, here's a set of data. We've constructed them to be basically the same sets of observations. And we can make the measurements. So this is just the spectral correlation function again, but I've actually put in bands where instead of comparing the fiducials to the simulations, I'm comparing the fiducials to a range of the observations. And what this tells us is we are roughly in the right place. We can also compare the observations to each other under this measurement. What's interesting about this is we see a good similarity under these measures. You'll see that the tracks between Ophiuchus and IC348 actually match each other pretty well as we compare them each to the different sets of the simulations. So we find a good set of tools. Almost all of these tools are turbulence-based. We are most sensitive to changes in Vero parameter and Mach number, as you'd expect, but also the driving scale. The interactions can be the most significant things that we detect. And we say that under this notion of experimental design, we really need to look at the entire parameter space. So next, we're actually going to use some tools in the experimental design to look at other responses. This Latin hypercube model allows us to probe interaction effects without running all of the simulations. We're switching to Orion because Enzo's given us some problems. We're going to actually look at more observed data, and in the spirit of question mark, profit, we'll then tell you all of the underlying physics of star formation. So if you'd like to try the code, it's here on GitHub. It's largely been tested by outside users, so it is usable. And I'll take any questions and or eat pizza. Thank you very much.
Okay, let's take just a couple questions and then we'll move on to pizza. I do not know who.
Simulations, but sacrificing the quality, is that a root grid of 128 cubed isn't going to give you a proper inertial range. It's too low resolution, and so all of these turbulent diagnostics will be extremely sensitive to that. So I was wondering if you've done some higher resolution tests.
Yes.
Sacrificing some of the parameter space.
No, but we've done the regression test to say, well, how bad are we with our thing? And then we sort of run it. So we run up to, we had 256, and we say, can we see this? It turns out that the resource to which I have access can't really handle the 512 root grid. As such, we push it out, we check the 256, and our results still hold here just fine.
Yeah, so, and then, a lot of the statistics fit, you have so many, but they're actually extremely complicated, and there's a lot of literature on each individual one.
Right.
So, like, for example, you showed the modified velocity centroids. It's well known that those are only sensitive to subsonic turbulence.
Right.
Supersonic turbulence. So it makes sense that you would have this crazy pattern
Right.
in your distance metric for that case.
Perfect. So this works, right? So we've basically said, don't use MVC on this problem. I'm not saying that, you have to remember that all of this measurements is not saying, oh, these are terrible methods. We're saying that they aren't useful for what we're trying to do, which is different.
So you talked about one aspect of their experimental design. There's also, whether you could change what observations you're taking to be more responsive to diagnosing whatever you want. So have you learned anything about that?
We haven't really explored the observation data set, though, this is clearly a case of when you have a hammer, everything looks like a nail, and I've thought about that for extensions here. So, yes, I think I love that idea.
Okay, one more very quick question. Go ahead.
So I'm assuming that the radiative transfer takes a lot less time than the actual simulation.
Right.
So have you tried looking at a given simulation at different viewing angles to see how the metrics change for that? Or do you have information about?
Yes. We haven't done much that was... we haven't done much. We've only done the different orthogonality. Or the different orthogonal faces, because we seed it with an initial magnetic field geometry. And so this is, in some sense, the only thing that's breaking symmetry here is the magnetic field orientation. And so we are looking at this from different angles as a way to measure sort of, do we have a handle on face orientation?
All right, if there are any more questions, I'm sure you can ask Erik. more people use them. All right, let's thank him again.
Week I had the flu.